in this series of advanced data structures and algorithms, we had started with the topic of hashing in our previous lecture, and today we are going to proceed with that particular topic only, in which we will be covering applications of hashing. Then we will be looking into some of the differences of binary search trees versus this hashing as in terms of data structures. Then we will be looking into some hash function and the properties, and then type. So this is going to be the agenda for our today's lecture. Let us begin with the applications of hashing. So now by this time you are completely aware that if we want a constant time searching, insertion and delete operations, at least on an average, if I am talking about, if we want a constant time search, insertion and deletion operation on an average, hashing is the solution, or we should go for hashing. It is, or we can say hash tables when we talk about. It is one of the most used or prominently used data structure for various problems. Which problems I am talking about? For example, if we want to find the duplicates, if we want to count the frequency of some particular items, or if we need to look for distinct elements, then in all these example problems we can use our hash table data structure. Now, looking into more detailed applications, let us consider applications of hashing one by one. So for example, first application which comes here in the list is database indexing. Database indexing says when you need to index and retrieve the data efficiently in the databases and other storage systems, because these databases are actually kind of large storage systems. So we can store the data here or the records in the database with the help of and not only store but retrieve data with the help of hashing. Then another common application which comes here is about dictionaries. That is to implement a dictionary to quickly search a word, because searching, as I have already told you, is going to be a kind of constant time operation. So dictionaries is one of the example problems or the applications in which hashing is very prominently used. Then if we want to store the passwords, hashing is used to store the password securely by applying the hash function to the password and storing the hashed results. So in the database or in the table of passwords, not the kind of plain passwords, not the plain text password, but the hashed result of the password is being stored, which is obviously going to provide some security. So password storage is another kind of application of hashing. Then next we will move on to cryptography. Cryptography is one of the area which is using your hashing a lot. I mean, there are huge usages of hashing in cryptography in order to generate the digital signatures or message authentication codes and key derivation functions. All these cryptographic problems are being solved by using your hashing functionality. Moving forward, we also have load balancing algorithms such as consistent hashing. These are used in order to distribute the requests to server in a network. Then apart from that, one of the kind of very new area, or which I can say it's kind of an emerging area, that is blockchain. Blockchain has the applications of hashing used in it. So hashing is used in blockchain technology such as proof of work algorithm, or to secure the integrity and consensus of the blockchain. You ultimately need some kind of hash codes. So blockchain is an application which is emerging, and it is relying heavily on the hashing thing. Then apart from that, we have image processing also, in which hashing is used in image processing such as perceptual hashing, which is used to detect and prevent image duplicates and modifications. So if the hash code of one particular piece of the image is different from the that particular image or the copy of the image, that means there has been a change or there has been a modification in this image, and that we can detect with the help of different hash codes, which again involves hashing. So then it is not only about the duplicates which are kind of related to image duplicates, it is also related to file comparison. For example, we have some hash functions which is for example SHA1, SHA1 or MD5. These are the hash functions which are there or which are used in order to compare and verify the integrity of files, that whether the file has been kind of disturbed or the contents have been kind of changed. Moving forward, we also have fraud detection as one of the applications of hashing. Hashing is also used in fraud detection and cyber security applications such as intrusion detection and antivirus software, and again it is used to detect and prevent malicious activities. So, fraud detection is also one of the examples or the applications. Then we have symbol table. Symbol table, as you all are aware, that's a table which is kind of generated by compiler in order to keep track of various variables, or we can say identifiers, and various identifiers are required to map to their different value in programming languages. So, that hash table is maintained, that symbol table is maintained with the help of hash table. Apart from that, we have caching. Caching is there always to store the frequently accessed data which is there, and the idea is to have the fast retrieval. So, for example, we have different browser cache, they use URL as keys and find the local storage of the URL. So, URL is given as the key, and then the local storage of the URL is being calculated with the help of hash and quickly loaded whenever it is required. So, browser cache is also there, which is going to use this hashing function. Then we have associated arrays which are nothing but the hash tables only. If you can see if you can see in detail, commonly SQL library functions allows us to retrieve the data as associative arrays, so that the retrieved data in the random access memory can be quickly searched for a key. We have seen lot many applications of hashing, including some fraud detection, image processing, file comparisons, cryptography, blockchain, then we have caching, symbol tables, and so on and so forth. Now, please recall that when we have started our hashing thing, so we started with the problem of searching, or we started with the problem of kind of number of comparisons, and in binary search tree as a data structure, we have the operations which are search, insertion and deletion in kind of order h in the order h time. These operations can be achieved. While when we talk about hash table, these hash table supports these insertion, searching and deletion in order 1 time, and the time complexity of the above operations in a self balancing binary search tree, for example, let us say an AVL tree or maybe an splay tree or maybe a red black tree, all these are self balancing binary search trees, that is basically order log n, or we can say order h. So, hash table seems to be kind of beating this binary search trees in all the common operations, but we have kind of a fair background to compare these two data structures. One is these hash tables and another one is binary search trees. So, all the keys if of a binary search tree we want in a sorted order, that can be done by just taking the in order walk of this binary search tree or in order traversal of a binary search tree. But as far as your hash tables are concerned, this is kind of not a very obvious or not a very natural operation, and that requires extra efforts. So here is something, or here is an usage in which your binary search tree is beating your hash tables, while the time complexity, if we talk about, of all the common operations like search, insertion and deletion, your hash table seems to beat binary search tree. But as far as all keys in sorted order is required, your binary search tree will help you here. By just having an in order walk of your binary search tree, you can have all these all the keys of binary search tree in a sorted order. So, with this effort, or with this kind of facility of sorted order, doing any type of order statistics, or finding the closest lower and greater elements, or doing the range queries is very easy if we have binary search tree BST as the data structure. Because sorting and all these kinds of order statistics are not the natural operations with the hash tables. Moving forward, if we can see, our binary search trees are easy to implement as compared to hashing, and these can be kind of we can say customized easily, or we can say without any much of the effort we can implement our customized binary search tree. But in order to implement the hashing thing, we need to rely on the libraries which are provided by the programming languages. So, customization of binary search trees is easy to be done at the programmer level, at the kind of programming level, in the sense that we can do it on our own without the help of libraries. But to implement the hashing, we need to rely on libraries which are provided by different programming languages. And we have also seen that with self balancing binary trees, all the operations work in order log in time, but for the hashing the average time is order 1. But with hashing, some kind of some operations are particularly very costly, and it is going to give you a complexity of order n, and this is the situation when the resizing is happening. So, when the resizing is happening, asymptotic analysis or even amortized analysis says, in the case of resizing, the amortized analysis says that these operations are becoming costly. So, if we talk about in general scenarios, if we have kind of space in our hash table, or our hash table is big enough to accommodate the keys, and we do not need resizing, your hashing is going to give you order 1 average time for the normal operations of searching, insertion and deletion. But as soon as this resizing happens, and you will move from size of table T to the size of table 2T, then this table resizing has to happen, and then these operations will become kind of costly, which is nothing but order n. Also, BST, if we talk about this, BST might turn out to be memory efficient as compared to hash tables, because for BST, if we talk about, let us say, n keys, we need to have exactly n nodes, no extra kind of a space, or no space overhead is involved here. But if the size of the hash, but as far as hash table or hashing is concerned, the size of the hash table can be larger for efficient operations. We have, let us say, a hash table of size 1000, and we are going to store, let us say, some keys, maybe a factor of maybe some 500, which is kind of an half of the thing, and half of the space is kind of, we can say, presently it is unutilized. This is not going to be a scenario when we talk about the binary search tree. We have exactly n nodes for n keys. So, that is one advantage of binary search tree as compared to hashing. Also, this binary search tree performs well on small data set, small data sets as in a small number of elements, where your hash tables being large in size or huge in size are not suitable for small data sets with a few elements. So if we need to work with very small number of elements, please prefer binary search tree as compared to hashing. Also, please notice that when we talk about binary search tree, it is having a recursive structure, which can be used to, because this is a tree, so every kind of non-leaf element or even a leaf element can be called as a subtree with either the empty children or with having children some value. So BST is basically a recursive structure, and this recursive structure can be used to solve the problems more elegantly and efficiently, while your hash tables do not allow for recursion. There is nothing kind of facility of recursion which we can kind of use or which we can implement in case of hash tables. That's not allowed, or that's not feasible, we can say, while your binary search tree is having a recursive structure. So till this point what we have seen is basically what are the kind of applications of hashing. We have seen some 10-12 applications of hashing, and then after the applications of hashing we have started with the comparison of binary search tree and hash tables, and we have seen a fair comparison in terms of space, in terms of various operations which are feasible, which operations are feasible with which kind of data structure and so on and so forth. So binary search tree versus hash tables we have seen. Now moving further, we are going to explore some of the kind of hash functions, but before directly jumping on to the hash functions, we need to look into what are the key properties of hash function, or what are the characteristics, what are the features that a hash function should possess. So when we talk about a hash function, let us have a quick recap or a quick recall that what actually this hash function is. So hash function, it's a type of mathematical operation that takes an input, or maybe a key, input here is a key, and it is going to output a fixed sized result known as hash code or hash value. So hash function is a mathematical operation which is operated upon a key. So input to that function or input to that operation is the key, and the output which it generates is is known as hash code or hash value. And please remember, I am insisting here on the word fixed size. Why I am insisting on the fixed size? I will be covering this in the upcoming features of the hash function. Now it must always yield the same hash code for the same input in order to be deterministic. So one thing which is very important for a hash function, that it should not change the hash code, or it should not change the output for the same input. That means it should be deterministic, and it should also produce a unique hash code for each input. This is kind of, we can say, it is something which is desirable, although it is not achieved always. We can have some situations in which hash code can be common for two of the inputs, but we can say that one desirable property of this hash function is they should produce a unique hash code for each input, and this thing is actually, or this is known as the hash property. Now the important features of hash function, if we talk about, then the first thing, as I have told you, that any hash function you choose should be deterministic. Deterministic means a hash function must always consistently produce the same output for the same input. It should not happen that if I am going to pass the same input twice the number of times, it is going to give me different results. It should not happen. So that means hash function must be deterministic. Then one thing which I just told you, that it should have fixed output size. So fixed output size is the output of a hash function, that means the hash code or the hash value which it is going to generate should have a fixed size regardless of the size of the input. So, whatever is the size of the input, the size of the output is always fixed. So, whether the size of the input is kind of 10 or whether the size of the input is going to be n, the size of the output must always be kind of fixed. Then your hash function should be efficient, that means it should be able to process the input quickly, and that is the kind of we can say bottom line feature when we talk about your hashing to be adopted as one of the fastest methods of searching, insertion and deletion. Then the hash function should be uniform, that means it should distribute the hash values uniformly across the output space to avoid clustering. Again, this uniformity is kind of an kind of a desirable property. Then we have one more property which is pre-image resistance. That means it should be computationally infeasible always to reverse the hash function, that is to find the original input given a hash value. That means if we are going to give the hash value, it should not result in the original key or in the original input. So, pre-image resistance should be there. Then apart from that, one more desirable property is it should be collision resistance. It should be difficult to find two different inputs that produce the same hash value, so should not be there. And also your hash function should be should have avalanche effect. The avalanche effect says a small change in the input should produce a significantly different hash value. So, even if you are changing your input even by 1 bit, the hash value should be kind of significantly different in order to avoid any kind of guess work to be done on the output of the hashing. So, in order to summarize this lecture, we have started from the applications of hashing, and apart from detailed applications of hashing, we have compared binary search tree with hash tables, and then we have looked into what actually a hash function is and what are the key properties or key characteristics of a hash function which it should possess. Now, in upcoming lectures, we will be looking into various types of your hash function. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next. Till then, take care. Goodbye.